All right, let's talk about something you've probably never thought much about: how we cut metal. It sounds simple, right? But it's actually an art and a science that is being completely turned on its head. And it all boils down to solving one fundamental make-or-break challenge.
You know, for anyone who makes anything out of metal, this is the million-dollar question. You've got to remove material as fast as you can to be profitable. But if you push just a little too hard, snap! You've just shattered an incredibly expensive cutting tool. It's this constant battle, this tightrope walk, to find the perfect sweet spot between speed and, well, destruction.
And it turns out, every single cut a machine makes is this delicate trade-off. It's a balancing act between two key things: how wide you cut into the material and how deep you go. Get this balance right and you're a manufacturing hero. Get it wrong and you're just making some very expensive scrap metal. Okay, so let's break that down. First up, we have what's called the Radial Depth of Cut, or RDOC for short. Honestly, the easiest way to picture this is mowing your lawn. The RDOC is just how much you overlap each pass with the mower. A bigger overlap means a wider cut, right? You're using more of the side of the cutting tool. So, if the RDOC is the width of your mow, then the Axial Depth of Cut, or ADOC, is the height. Sticking with our lawnmower, this is like how low you set the blades. A deep ADOC means you're using more of the tool's length, pushing it further down into the material with each pass.
Now, for the longest time, for decades, the playbook for this balancing act was pretty straightforward. It was basically an unwritten rule that everybody in the industry followed, especially when they had to remove a whole lot of material quickly.
This traditional approach was called peripheral milling, and the logic was simple. To rough out a part, you take a really wide but very shallow cut. So think a high radial depth, engaging maybe half the tool's width, but a very, very light axial depth. The whole idea was to just peel away these super thin layers, one after another.
An even more extreme version of this is called slotting. That's where you engage 100% of the tool's diameter trying to carve a channel in one single pass. Just imagine it. All the force, all the heat, all that pressure gets focused right on the tiny corner of that cutting tool. And that gets us to the fundamental problem with the old way. Both of these methods concentrate a massive amount of stress on one tiny part of the tool. And to keep that tool from snapping or literally melting from the heat, you really only had one option. You had to run the machine slow and steady. That was the only way. For generations, that speed limit was just an accepted fact of life in manufacturing. But in the modern world, efficiency is everything. So people started asking a pretty radical question. What if this whole wide and shallow approach is just plain wrong?
And that question led to high-efficiency milling, or HEM, and this strategy completely flips the script. Instead of going wide and shallow, HEM uses a very light radial stepover paired with a massive axial depth of cut. It's a totally counterintuitive way to think about it.
Just look at this. You can see the complete philosophical shift right here. Instead of a wide, shallow cut at a slow, conservative pace, high-efficiency milling does the exact opposite. It takes a much narrower cut, but plunges way deeper into the material. And here's the magic trick. Doing that lets the machine move at a dramatically faster speed, or feed rate. You're essentially trading width for depth and speed. So, how on earth does this work? Well, it's actually brilliant. By using that deep axial cut, you're no longer putting all that heat and force on one tiny corner of the tool. Instead, you're spreading that stress out along the entire length of the cutting edge, and with less stress on any single point, the tool can handle way higher speeds without failing.
So just how deep are we talking here? With HEM, it's possible to use an axial depth of cut up to 200% of the tool's diameter. Think about that. You're finally using the entire cutting edge that you paid good money for, not just the tiny little tip. It's a complete game changer.
And the benefits here are just massive. You're removing way more material, way faster. Your expensive tools last a whole lot longer because they aren't getting beaten up. And the key that unlocks all this is modern CAM software, which is finally smart enough to calculate these complex, super fast toolpaths. It's a win-win-win across the board.
Hey, don't just take my word for it. The source material for this explainer puts it pretty plainly. This combination can result in noticeably higher metal removal rates. Now, that might sound dry, but that one sentence represents a huge leap forward in productivity that completely changes the economics of manufacturing.
What's so incredible here is that a simple shift in thinking, one that was powered by smarter software, totally redefined a physical process that's been around for over a century. And it really leaves us with a fascinating question to chew on. As our digital tools get even smarter, what other rules of the physical world are about to be broken?